Okay, so this will be a short video on the enthalpy sign convention from a student who asked, how do we know what sign convention to use for our enthalpy integral based on the graph, our h versus t graph? And then which part of the question leads us to look up the values of h from the book? Okay, so using this example, this is a basic example of a couple of generic species. At a temperature other than 298, we are going to find our enthalpy of reaction, or H total, at 1200. And so a couple of different steps need to occur before we can conduct this reaction, or sorry, before we can conduct this equation. We need to find a known route from 1 to 2 uh, because it's not tabulated in the book at 1200. It is tabulated at 1298 or 298, but not at 1200. And there are other values that we can look up to help us get through these other steps. And because h is path independent, right, it is a state function, we can go through these other steps and come up with the same value as our h2 minus h1 here. And so to begin, uh, the first thing I would suggest you look up in the table is your H at 298, your endo or exothermic reaction. And you can do this step one because all of it is listed, tabulated in various tables. We have them here, and you'll note that this aluminum oxide is negative because it is releasing heat as it forms the bonds, whereas diamond um, is going to be requiring heat to form 1 mole of it. And so this is all joules per mole of the substance formed, right? Start with your equation and do your products minus reactants, which will tell you right off the bat whether or not you're endothermic or exothermic, and that will help start you on the right foot when drawing your graph. So let's say I know that this is exothermic, and that's the way I've drawn it, is that this reaction point at 298 is down. If it was endothermic, I would draw it up. And so um, I know that I'm going to be decreasing. And I didn't add any values here because I don't know what they are. It's just generic, right? Um, the next thing to look for is, do I have any phase changes? Let's say that alpha changes, sorry, not alpha, but A, substance A, changes from FCC to liquid at 700 Kelvin. Well, I'm above 700 Kelvin to start with, so I have to be starting with a liquid A, right? Uh, and then decreasing as I cool down to 298, I'm gonna go beyond or past 700, so I must be changing phase. And so I've looked up this value here. Let's just say it's 5 kilojoules per mole for the heat of fusion, um, and it's listed as a positive value, meaning that um, I would need to add heat to it in order to go from FCC to liquid, right? And that makes sense. Melting something requires heat. But because I'm going to be going in the opposite direction, this will be a negative value, right? And so we'll get to the equation there shortly. But the last thing you want to look up are your CP values. So you need to look up a CP, a specific heat for both of these phases because they're different depending on the phase. Some textbooks actually just fit one set of equation to both phases or multiple phases, but depending on what your source material is, you might need to look up two. And then you also need to look up for B and C. You look up their specific heats so that you can conduct your integrals, right? Uh, so knowing all of this, we're going to start by putting our first point high up on the graph, knowing that I'm exothermic, I'm going to be dropping. I'm going to be cooling to start with until I reach my phase transition temperature, at which point I will be going through a phase change, which I know will be releasing heat because we are going from a liquid to a solid, right? The table lists it as a solid to liquid, so all I'm going to do is add a negative up front, and then we are going to continue cooling. So let's take H1, H2, and H3 and look at them in the equation here. So H1, right, from 1200 to 700, the sum of all of my species times, or their moles of all the species times their corresponding CP values, conduct that integral. This is just a summary. It's actually going to be multiple integrals, right? And your cooling reactants from 1200 to 700 as you go from liquid to, or sorry, noting that A is liquid, so you use the right CP value. You then fuse, noting that this heat of fusion was listed as going from a solid to a liquid, so we're going to add that negative. And then continue to cool down to 298. Well, now that you've cooled beyond the transition temperature, make sure that you use the different CP for your face centered cubic version of A as you reduce down to 298. Once you're at 298, you can go ahead and conduct your reaction, right? And this is the number that you got to begin with because we started here actually. We're listing it as H4 because that's the step it shows up in this order of operations. But but we know that this is exothermic, and so we're right here now. So now we're reacting. We now have to use our equation to make sure that we have the right number of moles beginning and after the reaction before continuing, because we might have some additional reactants left over after we're done, and so you make sure to heat those back up to your final temperature so that we can compare our H total. And so, in summary, the general trend is that if you're moving down into the left, you're going to be cooling, right? And moving up into the right, you're going to be heating. Phase changes are noted by isotherms, and just remember that if you're going in the direction opposite listed in the book or in the whatever you're pulling the value from, that you need to add a negative. And then the heat of reaction really takes care of itself in terms of positive or negative. And then you can just sum up each of these steps, and because h is a state function, we will get the same number as if we had jumped right from 1 to 2. All right, well, I hope that helps, and good luck.